Hello everyone, thank you so much for attending this talk. This is a true honor to present our work here as one of the keynote presentations. It's unfortunate that I couldn't be with you in person because of some visa issues that I had, but I'm still so happy that with the great help of the technical committee and the local organizers, it's been possible to have the presentation virtually. So before I begin, I sincerely thank all the people who made this possible. Dr. Benny Rafael, Dr. Borja Garcia de Soto, and others. The title of my presentation today is BIM-based construction quality assessment using graph neural networks. My name is Navid Kayhani. I am a soon-to-be graduating PhD candidate at the University of Toronto and also a machine learning engineer at NASCA AI. This research was conducted jointly with Professor Brenda McCabe and the CTO and co-founder at NASCA AI, Dr. Bharath Sankaran. I'll be starting my talk discussing the problem that we're interested in, why it's important, what's missing, and how our solution can help. Then I provide some brief background about machine learning with graphs and graph neural networks. Next, I'll present our solution, BIM-GNN. We'll see some results and discussion about how this solution could be helpful. And finally, I'll conclude my talk by summarizing our key findings and also sharing some suggestions for future work. Let's get started. As we all know, construction is one of the world's largest industries, but the industry still faces certain challenges that makes it inefficient in many cases. For example, redoing or correcting work that has already been completed is common in construction, often because the as-built does not match the design. So having effective quality assessment and as-built verification processes are necessary to improve this situation. Performing this design versus reality comparison manually at a large scale could be quite complex and costly. The reality capture cycle is one systematic approach to automate construction control. So we collect on-site data, for example, images or 3D point clouds, process them to extract useful information, which is then documented or modeled in BIM and used for further informed decisions or actions. But the thing is, even with an ideal data capture solution, it's kind of impossible to guarantee complete on-site data because of high levels of noise and occlusions that we have on site. So the fundamental question that this research aims to address is how we could still reliably perform quality assessment as build verification while working with incomplete data. As a building block for project quality assessment, it's common that we evaluate the build status at the element level by comparing the elements in as-designed BIM with their registered 3D point clouds. On the right, we can see some examples of these correspondences and how they are affected by on-site noise or occlusion. For example, in A, we have a column that is covered by snow, which is noise here, and occluded by other elements, pedestal bottom and steel beam top. Or in B, the wall is occluded by the ceiling and some clutter on site. But most existing methods consider elements in isolation without considering the context. This results in inaccurate assessments in practice because of the on-site noise and occlusions. We argue that the incorporation of the project level context and semantic relationships between elements can actually be helpful in element-wise assessments. Take this as-built verification example in image D. Even if the wall in D is not fully captured in on-site data, observing the opening in it can imply that the container wall has been built and is not missing. But how could we incorporate this? We propose BIM-GNN, a novel approach to element-wise quality assessment that leverages semantics in as-designed BIM. It transforms BIM into a graph where building elements are nodes and their topological and spatial relationships are edges. We define the problem as classifying elements into 4 build quality status categories. Verified means element is built and matches the design. Deviated is when element is built but doesn't match the design. Missing means element is not built, and no data is there is insufficient information. Since we represent BIM as a graph, we need learning algorithms that can operate on graphs. Graphs are permutation and order invariant data. They can have arbitrary sizes and there is no spatial locality to them like text or images. So to capture their complexity, we would need particular machine learning algorithms. All these algorithms map the information in the graph domain to a vector in a linear embedding space. These learned vectors can then be used for downstream learning tasks such as classification, clustering, and generation at node, edge, or even graph levels. But how does this mapping work? Graph neural networks, GNNs, use message passing to update node representations by gathering information from neighbors. Each node's neighborhood defines its computational graph. Consider this example on this slide. We have a graph with node features on the left and the computational graphs for a two-layer GNN on the right. As you can see, nodes A and F have different computational graphs. To calculate the embedding of a node, for example A, at layer 2, we need to calculate the embeddings of its neighbors B and C at layer 1 using their initial embeddings or features. At each GNN layer, node embeddings from the previous layer are transformed using a message function to calculate what is called or referred to as message. These messages are then aggregated using a permutation invariant function like sum or average to update the node embeddings in the next layer. Now let's focus on the details of our solution. BIM-GNN inputs as designed BIM in IFC format, element-wise 3D point cloud correspondences, and a set of known labeled elements. It first transforms the BIM to a graph using the BIM to graph module, and then augments the graph with node features and labels. Node features include scan-based, graph-based, and BIM-based features. Scan-based features include hand-engineered baseline ML features and learned PointsNet features. BIM-based features include element type and floor, and graph-based features contain extra information about the graph structure, for example, node degree, node centrality, and so on. So we have a graph that we know the labels of some elements in it and want to predict the labels for unlabeled elements. And we used a semi-supervised transactive learning settings to capture project level context. So we train our BIM-GNN classifier on the same graph to classify the elements with unknown labels to our 4 build quality status categories. To represent BIM as a graph, we consider 2 types of relationships in the BIM to graph module. We have topological relationships that are extracted directly from the IFC structure, and then we have spatial relationships that are based on the distances between the elements' bounding boxes. As discussed, we define our problem as node classification. We have access to the graph structure, node features, and the labels of some elements during the training, and the goal is to predict the labels for the rest of the nodes. We use graph attention layers, or GATT convolutions, from the graph attention network paper. We use GATT because of its ability to learn node importances through attention mechanism. Our model has a sequential architecture and consists of 2 multi-headed GATT convolutions and a fully connected layer with ReLU activation and dropouts. Now let's look at the results. The dataset that we used in this work contains data from 3 institutional building projects, including 2 process scans, or what we call analysis, from a university building, 1 from a hospital, and 1 from a school project. Each analysis was then converted to a graph. As you can see in the table, The edge counts varied between tens to hundreds of thousands, but the extracted relationships turn out to be dominated by the spatial relationships across all analyses. This is because IFC-based relationships can easily be affected by the way information is modeled in BIM. And in practice, we don't necessarily see a unified modeling style, and therefore we may get no or limited IFC-based relationships. The figure on top shows the distribution of ground truth labels for nodes in each graph, and we can observe an imbalanced label distribution across analyses. In our experiments, we used 9 randomized splits. We split the nodes in each graph with 60% training, 20% validation, and 20% test, considering all the 3 feature sets of scan-based, graph-based, and BIM-based. We compared our results with a baseline model that we call ML Vanilla. ML Vanilla consists of an ensemble of supervised models with no semantic incorporation. It was trained on the scan-based features using way more elements from various projects. We chose the F1 score with weighted average as the metric for evaluation since it is suitable for evaluating both balanced and imbalanced datasets. F1 score is a harmonic average of precision and recall, is between 0 and 1, the higher the better. The table compares the performance of our model with the baseline model per analysis, and the figure on the right provides an overall comparison. As you can see, our results suggest that our model outperforms the baseline significantly with an average F1 score improvement of 22% and by achieving a lower variance in performance. In another experiment, we performed an ablation study. The goal is to investigate the importance of the features by removing one feature or feature set at a time from the original dataset. Observing degraded performance means that the ablated or the removed feature positively contributes to superior performance of our model and is indeed useful. The higher degrade in the performance after ablation, the higher the feature importance will be. So the most important feature will show up in the far right. We removed pointed features, element type, graph-based features, ML baseline features, and finally the whole scan-based features. So except for pointed features, all the features positively contributed to the model's expressiveness, while scan-based features were the most important ones as expected. But let's revisit this more closely. This comparison means that our model could still outperform the baseline even without the scan-based features, essentially with no on-site data. This is the case if we have access to 80% of the labels in an analysis, 60% for training and 20% for validation. On top of that, we need to have access to graph structure and the other 2 feature sets. This property of BIM-GNN could be so useful when we are dealing with partially observed or unobserved elements. So far, we assumed that we have access to a high percentage of labeled data during training, and we showed that we could outperform the baseline model given this assumption. But how should we obtain these labels in practice? And what happens if we have access to a lower percentage of labeled elements for each analysis? To answer these questions, we decrease the percentage of available labels with the same ratio of training to validation elements and repeated the experiments. Results show that even with 10% of the nodes, 7% training, 3% validation, our method BIM-GNN can still achieve a considerably higher F1 score than the classical approach, the baseline. In conclusion, in this work, we demonstrated that by exploiting the semantic relationships in BIM, we can improve element-wise construction quality assessments. Particularly, we showed that IFC-based relationships might be unreliable because they are dependent on modeling practices. We also showed that BIM-GNN, our solution, outperforms classical methods by considering semantics and context rather than treating elements in isolation. We showed that BIM-GNN enables the prediction of unobserved elements based on the known status of some related observed ones. To enhance our approach, we plan to explore additional graph learning algorithms. We want to incorporate more relationship types to better capture the relationships between smaller objects like MEP elements. Additionally, we would like to add relationship types as edge features and further evaluate the generalizability of our method by applying it to more projects because we use only 4 analyses from 3 projects. And finally, we recommend that researchers add temporal relationships in 4D BIM to predict element labels based on time and sequence-dependent context. With that, I end my presentations and I'll be more than happy to take questions. But before that, I would like to thank all the colleagues and friends at NASCA AI, University of Toronto, and our financial supporters, MyTax, ISARC, and Human Tech. Thank you so much.